This is the video for section 7.5. In this one, we're talking about applications of vectors. The first application we can talk about is called the equilibrant. So the equilibrant of any vector is just the opposite of the vector. In the last section, we were talking about the resultant of two vectors, which is where you add the two vectors together. The equilibrant of two vectors is just the opposite of the resultant. In this picture, we've got vector A and vector B. A plus B would be the resultant. The equilibrant would be the vector with the same magnitude as this, but going in the opposite direction. So our equilibrant vector would be this one going in the opposite direction as the resultant, but it's going to have the same magnitude. So we could write this as the opposite of A plus B. In this example, we've got two forces, 54 newtons and 42 newtons. They're both acting on a point A. We know the angle between the two forces is 98 degrees. And what we're trying to find is the magnitude of the equilibrant. So really what we could do is just find the magnitude of the resultant vector. The magnitudes of the resultant and the equilibrant are going to be the same. This is really what we want to do to start with, is find the magnitude of the resultant. So I'm going to draw these two in the plane since we just know the angle between the two. I'm going to put the 42 Newton force as the one on the horizontal. So that this point is 42, 0. I know that the angle between my forces is 98 degrees. So if I'm going from here 98 degrees, it's going to go just a little bit past the 90-degree line. And my magnitude for this force is 54 newtons, so it's longer than this one was. So I've got my angle here is 98 degrees, and this length is 54 newtons. It's because I've started both of these vectors from the same point. I'm going to go ahead and draw the parallelogram. My resultant vector would be the diagonal of my parallelogram. What I really want to look at is my equilibrant, so it's going to be this vector flipped around. So here's my equilibrant vector over here. Now if I want to find the magnitude of my resultant vector, there are two ways I could do this. Since I've already got the components for this one, I could find the horizontal and vertical components for this one, add the two together, and then find the magnitude that way. Or I could set up my parallelogram and use the law of cosines. Since we already have the components for this one, let's just find the components for this one. So the components of the 54 Newton force for the A, that's going to be 54 times the cosine of 98 degrees. And notice that's going to be negative because this went just a little bit past the y-axis. For the vertical component, that's going to be 54 times the sine of 98 degrees, and that's approximately 53.474. So if I add my two component vectors together, I'll get my resultant. What I really want is the equilibrant, so it's just going to be the opposite of that. So I'm going to take the opposite of the sum of these two vectors. When I combine these two, I'm going to get 34.485 approximately, and these two, I get 53.474. Now since I'm doing the equilibrant, I'm going to distribute my negative sign. So then both of my components are negative. And that fits my picture because this would actually be in the third quadrant if we're thinking of this being in the plane. To find the magnitude of this, I'm going to use the rule that the magnitude is the square root of a squared plus b squared. That means I'm going to square both of my components. And remember, when you square a negative number, you get a positive number. I'm going to get approximately 63.6 for my magnitude. That's the magnitude of the resultant. It's also the magnitude of the equilibrant. Now to find the direction angle for my equilibrant, we've got the tangent of theta is equal to b over a. So that would be negative 53.474 over negative 34.485. Since this is going to come out to be a positive number, when we do inverse tangent, we're going to get an angle in the first quadrant. We get approximately 57.2 degrees. So that's really the direction angle for our resultant. Now for our equilibrant, that's another 180 degrees past that, so we're going to take our 57.2 and add 180 degrees, and that gives us 237.2 degrees for the direction angle for our equilibrant. Now some other kinds of applications we can do with vectors are ones that have to do with inclines. And this is talking about the force that's necessary to keep something sitting on an incline. So it has to be enough to counteract the force of gravity that's going to make the object slide down the incline. In all of these problems, we're ignoring the force of friction. So if we've got an object that's sitting on an incline, the force of gravity acts straight downward, but it's really the resultant of two other forces. One of them acts parallel to the incline and down the incline, and the other one actually acts perpendicular to the incline. The force required to keep the object in place on the incline is the equilibrant of the force vector that acts parallel to the incline. So it's the equilibrant, or in other words, the opposite of this force. So we're going to do this to find the force required to keep a 100-pound wagon parked on a hill that makes a 32-degree angle with the horizontal. So we have the force of gravity that acts straight downwards from the wagon, and the magnitude is the weight of the wagon. So the magnitude of our force of gravity is 100 pounds. And I'm going to call this G for gravity. Then our two components of the gravity force are one that acts parallel to the incline and another one that acts perpendicular to the incline. So really what we're going to do is draw a little parallelogram with these two vectors. The gravity force is actually the resultant of these two components. I'm going to call this vector G1 and this vector G2. So our total gravity force is actually the G1 plus the G2. And what we're trying to find in this problem is the G1. The actual force we're looking at would be acting in the opposite direction to this one. So it would be acting up the incline, but the magnitudes will be the same. Now in this one, since these two were perpendicular to each other, then we've got some right triangles in here. We know that this angle is 32 degrees. This is a right angle. That means that this angle and this angle right here are complements, so that would make that one 58 degrees. And then this is also a right angle, so this angle is 32 degrees. So it turns out that this angle is the same as this angle. Here we've got a right triangle. We have the hypotenuse is 100 pounds, and what we're trying to find is the length of this side, which would be the magnitude of our G1. This side is actually opposite our angle of 32 degrees. So the sine of 32 degrees would be this magnitude divided by our hypotenuse, which is 100. That means the magnitude of our force that we're looking for would be 100 times the sine of 32 degrees. That would turn out to be approximately 53, and our units were pounds. Here's another similar problem. This time we know the force that's required to hold the crate on the ramp, but we want to know what the angle is that the ramp makes with the horizontal. We've got the force of gravity, which is going to act straight downwards. And then we have our two components. One is acting down the ramp, and the other one is acting perpendicular to the ramp. The gravity is actually the resultant of those two. I'm calling these G1 and G2 just like I did for the last one. This time I know the force required to hold the crate on the ramp is 18 pounds. That would actually be the force going this direction, but it would have the same magnitude as this one. So this magnitude is 18 pounds, and we know the force of gravity magnitude is going to be 74 pounds. What we're trying to find is this angle that the ramp is inclined at. What we saw in the last problem is that this angle and this angle turn out to be the same. So this in here is angle theta. This side of our triangle is 18 and this side is 74. This is the side opposite our angle. So we would have sine of theta would equal 18 over 74. We're trying to find the angle, so we could do the inverse sine of 18 over 74, and that would give us our angle theta. And that turns out to be approximately 14 degrees.